Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 7, Differential Equations. Today's topic is 7.6, General Solutions Using Separation of Variables. Enjoy today's notes. All right, everybody, welcome to 7.6, Separation of Variables. We're finding some general solutions. This is a topic that is super useful for students, obviously in AP Calculus, but also for AP Physics. Any students that are taking calculus-based physics, being able to do this separation of variables technique is incredibly useful. So maybe we'll have some of those students joining us as well for these videos today. But to start off, we're going to recall implicit differentiation. You might remember that this is a topic that we talked about way back when in section 3.2. So chapter 3, Section 2 was this topic on implicit differentiation. And the idea back in Chapter 3 was that we are taking the derivative of an equation with respect to a certain variable. So for example, what this might have looked like is I could say that I'm taking the derivative with respect to x of each of the three terms inside of these square brackets. Here in this case, when I'm taking the derivative of x squared, that's going to give me 2x. And because the variable of x squared matches with the variable that I'm taking the derivative with respect to, I end up with just a 2x. Nothing special there for this piece. If I move on to the next piece, if I take the derivative of my y squared, that is going to give me 2y. But because the variable in this expression is y, and that does not match the variable from which I'm taking the derivative of, I'm going to end up with this extra dy dx term, the derivative of y with respect to x. Here on the right side, this equals 9. Because this is a constant, when we take the derivative of that, that's going to be equal to 0. And then frequently what we did once we took the derivative with respect to x, is we would frequently try to get dy dx by itself. So in this case, we would subtract 2x from both sides. That would give me that 2y times dy dx is equal to negative 2x. And then I would divide both sides by 2y to get that dy dx by itself. And so that tells me here that dy dx is going to be equal to negative 2x divided by 2y. We might simplify here, seeing that the 2's would cancel each other out. So dy dx would be equal to negative x over y. And that would be our expression for, our equation with this implicit differentiation. So the idea for today of the separation of variables is like implicit differentiation, except backwards. So there's a general process for these. What we'll notice is that, here in the original problem that we were looking at, we had an equation that didn't have any derivatives of it, and we took the derivative, right, with respect to a certain variable. In today's problems, we're doing the backwards of it. We're told that the derivative is equal to some expression. Frequently, it's got x's and y's, and the goal is to go back and find out what y needs to be. Now, in this process of separation of variables, it is frequently the same process most times. So we're going to talk about how to do it, and then we'll try to explain what that process looks like here. But the name of the way that we're doing this is called separation of variables, and that's because it's our first step in this problem. I want to get everything that has a y on the left side, and I want to get everything that has an x on the right side. Now, we frequently think of dy dx as one thing, right? This is the derivative of y with respect to x. But for the sake of this process, what we're going to do is we're going to actually imagine that these are two different things, that this dy and this dx, these differentials, are two separate parts. And I'm going to treat this dx like something that's being divided by that dy, and in order to move that to the other side, because it's dividing, I'm going to just multiply by dx on both sides. What that does here is it's going to give me that dy is equal to x squared over y times dx. Now again, I'm trying to get all my y terms on the left, I'm trying to get all my x terms on the right. So because I've got this divided by y over here, what I'm going to do now is multiply that y on both sides of the equation. And what that's going to give me is y dy is equal to x squared dx. So at this point, I've now successfully separated my variables. All the y's are on the left, all the x's are on the right. My next step, what I'm going to do is I'm going to take the integral of both sides. So the integral of y dy is going to be equal to the integral of x squared dx. Now at this point, what we can do is we can use all of our knowledge from chapter 6 about how to take an antiderivative. And we know that because this is a y to the 1, that we could use the power rule and we can add 1 to that exponent and divide by that new exponent. If we do that, that's going to give us y squared over 2 is equal to the antiderivative of the right side of this equation. Because it's an x squared, we're going to add 1 to it, so it's going to become an x cubed, and we need to divide by that new exponent of 3. Now, you might remember from back in chapter 6 that when we take an antiderivative and there are no limits of integration, like we see here, that we end up with a plus c when we do it. Because there's a constant on the left side of this equation and a constant on the right side of this equation, when I take that antiderivative, we can essentially, in cases like this, treat it as if there's just one total overall constant. And so after I've taken the antiderivative of both sides, I'm going to add a plus c on the right side. And again, like this is taking into account essentially there's a c on both sides, but if we were to move both of those c's to the right side, there would be some constant on the right side that we don't know. Next, now that we've taken the antiderivative, I want to get this y by itself. So my goal here is to figure out what do I need to do to get y by itself. We do some algebra. Here I can see that we can multiply by 2 on both sides, and that's going to give me that y squared is equal to 2 times x cubed over 3 plus 2 times c. C is a constant. If we multiply it by 2, it's going to still be a constant. So I'm going to leave that as just c over here on the side. Technically, these c's are different, right? This one's twice as large as this one, but it is still some constant that we don't know. Next, after that, we are going to want to get this y by itself. So we're going to take the square root of both sides. Because we're taking the square root of both sides, we're going to end up with a plus or minus on the right side of this 2x cubed over 3 plus our c. And this would be sort of our explicit equation for what y would be for this situation. There's a positive version, there's a negative version. Sometimes later this week and later in further sections, we're going to talk about how do you know whether it's positive or negative. But for now, since we don't know what c is and we don't know what points it's going through, this is where we're going to stop for this problem. So generally, what I do want to do is I want to talk about what this process looks like. So again, the first thing that we did back here at this first step is we are separating the variables. So separate the variables first. So that means that we want to get all the x's on one side and all the y's on the other. That's what we did here in this first step. Next, we're going to take the integral of each side. So take integral of each side. That's our step 2 here. After that, sort of step 3 is you want to get the y by itself. And so that was our step 3. After that, the rest of this was essentially algebra that we were getting that y by itself for this equation. But frequently, pretty much many of these problems with separation method are going to be these 3 steps that we're going to do each time. Great. Let's take a look at number 2. Problem number 2 says dy dx is equal to sine of x times y squared. Similar to our process over here, the first thing that I want to do, I'll just put sort of a 1 for showing where the step is I want to get the variables of the same type on each side. First, I'm going to multiply by dx on both sides. So that's going to give me here that dy is equal to sine of x times y squared times dx. So we move that dx to the right side. I want this y squared, though, to be on the left side. So since it's multiplying by that sine of x, I'm going to divide by sine of x. And by doing that, that's going to give me essentially 1 over y squared dy is equal to sine of x dx. So I was dividing by that y squared on each side, so it's in the denominator. We could say dy over y squared, but it's going to be a little bit easier to write this as 1 over y squared. But again, we got all the y terms on one side, we got all the x terms on the other, so step 1, separating the variables, is done. Next, step 2, we're going to integrate both sides. And so what we can do here is I'm going to rewrite my 1 over y squared as y to the negative 2 dy. That's going to help me take my antiderivative. And then the integral of sine of x dx. If we do that, again, on the left side here, we can do the power rule. We can add 1 to that exponent, so that negative 2 is going to become a negative 1. We need to divide by that new exponent, which is our negative 1 here. And then we're going to say that's equal to the antiderivative of sine of x, which if we think back to what that is, that's going to be negative cosine of x. Again, we're going to add that plus c on the right side of this equation. Again, technically there are 2 different c's, but we're going to just combine them all on one side of the equation when we do this. So that's going to be right here. All right, so that's the end of step 2. What does step 3 look like? We're going to start trying to get y by itself. So here for step 3, what I'm going to do on the left side is I'm going to rewrite this y to the negative 1 over negative 1 as negative 1 over y is equal to our negative cosine of x plus c. After that, what I'm going to do is I'm going to get rid of the negatives on both sides, essentially divide or multiply by negative 1 on both sides to give me that 1 over y is equal to positive cosine of x. Technically, that's like a minus c, but again, it's a constant, so we're going to just leave it as a constant for this. And then because this is a reciprocal, in order to get the y by itself, I'm going to take the reciprocal of both sides of this equation. And so that's going to tell me here that y is going to be equal to 1 over cosine of x plus c. And that would be our equation for y in this problem. Again, recap of those steps. We separated the variables first. We got all the y's on one side. We got all the x's on the other side. We then took the integral of both sides. So we found that antiderivative of each of those parts of that equation. And then after that, we got the y by itself to find out what that explicit equation was going to be. And that turned out to be 1 divided by cosine of x plus c. Great. We're going to move on to number 3. Let's see some more of these. So for problem number 3, we've got dy over dx is equal to xy. Again, what we're going to do first for that step 1 is we're going to try to get the variables all on one side, or rather all the x's on one side and all the y's on the other. So if I multiply by dx on both sides, dy equals x times y times dx. And then we could divide by y on each side. So we get 1 over y dy is equal to x dx. So that's the end of my step 1. We've got all the y terms on one side. We've got all the x terms on the other. Step 2, we're going to now integrate on both sides. So the integral of 1 over y is equal to the integral of x dx. 1 over y is one of our special integrals. We know in this case that we actually can't do the power rule because this is like y to the negative 1. This is one of our special rules that the antiderivative of 1 over x or 1 over y is the natural log of the absolute value of that variable. So the natural log of the absolute value of y is going to be the antiderivative of that left side. Again, this is some review from chapter 6. And then here on the right side, because it's an x to the 1, if we do the power rule, that's going to give me an x squared over 2 when I take that antiderivative. Of course, we have a plus c on the right side of our equation. So now that we've taken the antiderivative of each side, step 3, we're going to now try to get that y by itself. But this one's a little bit interesting because the y is inside of this natural log. And we have to think about what would cancel a natural log out. So this is a little bit of review from pre-calculus or maybe honors algebra 2. But if we think about what cancels a natural log out, it's actually like an e to the x function. And so technically what I'm going to do is I'm going to take e to the left side of this equation and e to the right side of this equation, and we're going to see what cancels out. I'll show my work here to show you what that looks like, but we've got e is equal to e. And so this is e raised to the natural log of y is equal to e raised up to the x squared over 2 plus c. So notice that both of these are in the exponent of these e's. Now the idea here is because e and natural logs are inverses, they're going to cancel, making the left side of this equation just the absolute value of y is equal to the right side of this equation, which is e raised to the x squared over 2 plus c. And what we can do then, is two things to try to get this y by itself. Because this has an absolute value on it, we know that y could be positive or negative for this. And so when we get rid of that absolute value, what that's going to do is it's going to add a plus or minus on the right side of that equation. So by getting rid of these absolute values on the left, I have to add a plus or minus here on the right side. Also, though, what we can do is we can use one of the properties of exponents to bring down this constant as a coefficient of our e. And so one of our properties of exponents says that if you have two things of the same, two things that are being added in the exponents, that we can rewrite that as two things of the same base that are being multiplied. But ultimately what this ends up giving us is plus or minus c times e to the x squared over 2. And so this x squared over 2 is in the exponent of that e. But this would be our equation here for problem number 3. So plus or minus c times e to the x squared over 2. Now again, I would say explicitly here, this is the type of problem we see most often in like AP Physics when we're doing the separation of variables. Frequently they will have these natural logs, and in order to get rid of them, we need to raise it to the e on both sides. Though the e and the natural log cancel out on the left, and then we'll end up with an answer that has an e with an exponent of some function in it. Pretty much anytime that plus c is in the exponent, you're going to bring it down to the front. And I'll just say, like, if this is free response, you could leave the c in the exponent, but most of the time on the multiple choice for the AP exam, they will have brought that c down to the front as a coefficient for the e. Great. That's problem number 3. Number 4, we've got dy over dx is equal to 2xy plus 4x. So in this case, if I'm trying to think about, we know that step 1 is that we're trying to get all the y's on one side and all the x's on the other. Problem here is that I have an x and a y here in one term. So if I were to like subtract that over to the left side, well, I'd still wouldn't have my variables separated. So I need to think about, is there anything that I can do that would actually separate the variables in this case? And what I notice here is that, well, actually both of these terms that are here have an x in them and multiples of 2 as the coefficients. So my first step here, even before I start doing the separation of variables, is I'm going to say, okay, well, dy dx is equal to, if we factor the right side here, that's going to be 2x times y plus 2 on the right side. All right, and we say 2x times y would be my 2xy, 2x times 2 would be my 4x. So it's the same thing, just factored. But now the nice thing is I can actually divide by this y plus 2 term to get that to the left side, and then multiply by dx to get that to the right side. If we do that, we're going to end up with 1 over y plus 2 times dy is equal to 2x times dx. Again, I multiplied my dx to the right side, and then I divided by y plus 2 to get that to the left side. All my terms with my y's are on the left now. All my terms with the x's are on the right side now. So we're ready to move on to step 2. Step 2, we're going to take the integral of both sides. So actually, I add that to this step here. In this case, this 1 over y plus 2 is of that same form of like 1 over x. When we take the antiderivative of that, we're going to end up with the natural log of the absolute value of y plus 2. And on the right side, if we do the power rule, we would add 1 to our exponent here to make that an x squared, and then divide by 2. So those 2's would cancel, giving me just an x squared plus c on the right side when we take that antiderivative. Same ideas in the problem here on the left side. If I want to get this y out of the natural log, in my step 3, now that I've taken the antiderivative, we want to get that y by itself. And what I'm going to do is I'm going to raise e to both sides of this equation, e to each of those equations on the left and the right. So e raised to the natural log of y plus 2 is equal to e raised up to the x squared plus c. Again, e and natural logs are inverses. They're going to cancel each other out, giving me now just the absolute value of y plus 2 is equal to e to the x squared plus c as an exponent. And in order to get rid of these absolute values, we can add a plus or minus here on the front of our equation. And so that's going to give me y plus 2 is equal to plus or minus e to the x squared plus c. Same as in the last problem, though, what I'm going to do, because I've got a c in the exponent of this e equation, I'm going to use one of my exponent properties and bring that c down to the outside of my e. So we've got y plus 2 is equal to c times e to the x squared as its exponent. Now here in this step, because c is a constant and because it's in the front, we don't actually care whether it's positive or negative. Essentially, this plus or minus that we had here is it's like inside of the c. The c could be positive or negative, and so now that the c is here, I don't actually need to bother writing that plus or minus here because the c could be positive or negative. We don't know in this case. But last step here, if we want to get that y by itself, we're going to just subtract 2. So our final equation for this looks like it's going to be y is equal to c times e to the x squared, all subtracted by 2. And so that would be our final answer for problem number 4. Same as with the rest of these, we've got some great practice problems over the next couple of pages. Please try them out, check the solutions, and then check in with your teacher if you've got any questions. Hope you have a great rest of your day. Take care.